Welcome to the massive open online course on Aspen Plus. In this lecture, we are going to discuss how to model a dryer. The dryer is a process equipment which is used to remove moisture content from a load of solids. The moisture may be simple water or some volatile liquids such as alcohol. Let us first understand how a dryer functions. Dryer evaporates volatile moisture component from solids by applying energy supplied by hot gas streams, heated surfaces, or more rarely by some other methods such as dielectric heating. The dryer model of the Aspen Plus software can handle multiple conventional moisture components with any combination of heating methods. The dryer can be of many types, but in Aspen Plus software, mainly there are 4 types of dryer calculations, namely the shortcut method, convective dryer model, spray dryer model, and contact dryer model. The shortcut model, it calculates the heat requirement and the condition of exit streams from the specification of exit moisture content. That means, suppose you have a wet solid that is having 10% of moisture content, and the exit moisture content should be anything which is equal or more than the equilibrium moisture content. Moisture content in exit solid cannot be 0 because there will be always some moisture left out, that is called equilibrium moisture content. Suppose it is 0.02. That means you do not want your exit solid to have more than 0.02% moisture content. So in this case, your feed moisture content is 10% and exit moisture content is 0.02%, and you have to specify this exit moisture content, that is your requirement, and obviously you have to feed in the feed data, that is what is the feed composition, feed rate, feed temperature, feed pressure, etc. So model will calculate the heat requirement and the condition of the exit streams. But it does not attempt to predict any drying performance based on drying rates. You might remember what is drying rate. So drying rate can be obtained from these drying curves. Here you can find the drying rate, temperature versus time. So how the drying progresses with time, this is the initial period, and this is constant drying rate period, and this is falling drying rate period. This is described over here in the Aspen Plus help file, but you can also refer some good textbooks like Treble's Mass Transfer Operation book, and you can find more information from there. You can refresh your knowledge. All these things are taught in the undergraduate level of chemical engineering, so most of you already know it. But in shortcut calculation method, this drying rate is not used for drying performance calculation. The second calculation method is convective model calculation. It is the model of convective dryer. You might already know how a convective dryer works. Convective dryer looks like this. From one end, send the solid, that will be wet solid, that will go in from one end, and it will come out from the other end, which will be dry. So it will be passed through a conveyor belt or something, and there will be some drying medium, mostly air. So air will be passed from this end, and it will come out from this end. And while flowing, inside the convective dryer, both the solid and the gas, they come in contact with each other, and thereby the gas picks up the moisture content from the solid and eventually the solid gets dried up. And this moisture will be carried away by the gas. So that's how the convective dryer functions. And convective model performs the calculation based on the drying rates. A few minutes back, we discussed about what is a drying rate. For typical convective dryers where the wet solids come into contact with the hot gases. That's what exactly I explained. And then comes the spray dryer. Spray dryers are used to form solid particles by dispersing a solid liquid mixture or solution into small droplets in heated gas. So here also heated gas is used and evaporating the liquid from those droplets. Now let me give a small description about how a spray dryer works. Spray dryer will be something like this. It's a chamber. The heated gas will be flown from the bottom, and from the top you will find some nozzles, and this nozzle will disperse the liquid into some small droplets, and these small droplets will be sprayed through the nozzle. It will come down, and while it comes down it will come in contact with this gas, and thereby the liquid portion of those droplets will be evaporated and only the solid portion will remain, which will form some solid particle or some porous particle. All the solids will be collected from this end. The gas will be thrown out from the other end. So that's how the spray dryer works. The configuration of spray dryer will be a bit different from application to application, but overall idea is the same. And finally, the contact dryer. The contact dryer dries solids by heating them by direct contact with hot surface. So in this case, the energy is supplied by the hot surface, and hot surface radiates heat, and that heat is fed to the wet solid, and the moisture content of the wet solid is evaporated thereby. So evaporating moisture which accompanies the solid. It can also be used to model other types of dryers with indirect heating, where rate of heat transfer to stream is known. Indirect heating, there are many examples. Some of the examples are there in our household application, such as microwave heating or induction cooker. So they are kind of indirect heating. So these are the types of dryer calculation methods that we have. Now let us go to the Aspen Plus simulation window to learn them better. In Aspen Plus simulation window, in the model palette, you will find it in the solids tab over here. So this is the dryer block that you have to use. There are various icons. Although icons doesn't matter, whichever icon you use, the procedure will be same. But just to give a feel of the type of dryer you are using, for instance, this looks like a convective dryer, and here you will find the conveyor belt which carries the solid, and the heating gas is fed through this nozzle and it goes out from this nozzle. And if the conveyor belt operates clockwise, then it is co-current fashion. At least for this particular picture, it is co-current fashion. If it operates in the counterclockwise direction, then it is a countercurrent model. Similarly, you can use this icon for spray dryer. You will find a small nozzle over there which is dispersing the liquid droplets. So this is the spray dryer icon. And these two icons are used for contact dryer. So let us choose this one. You will find two mandatory material streams. This is a mandatory input, that is feed. Feed means the solid feed, which is wet solid feed. And this is the product stream. Typically it should be dry product stream. So this is the mandatory thing. Now there are optional inputs like Here it is inlet gas. It is optional. For shortcut dryer calculation, you do not need this stream. Okay, but for spray dryer or for convective dryer, you will need this inlet gas. That is inlet gas and the separate exhaust stream. So these two things will be needed for spray dryer and convective dryer. And there is another second inlet gas stream also is there, which is optional. So we can explore them further. Now let us open the block. There are plenty of specifications that we have to set. There are two types of operations. One is continuous operation, another is batch type of operation. Now if you choose continuous type of operation, then there will be 4 types of dryers that will be open for you. One is shortcut dryer, convective dryer, spray dryer and contact dryer. I have given short description of them all. We will learn better when we discuss it further. But if you choose batch dryer, then you will have only one option, that is convective dryer. Now let us first discuss continuous shortcut method calculation. Here you will find that you have to specify the pressure and one of these 4. Either you have to specify the heat duty or superheat or temperature change. Okay. Pressure is the mandatory parameter that you have to feed in. Heat duty, you can say that I am feeding in 50 kilowatt of heat to knock off the moisture that is there in the wet solid. So you have to give that input. Or if you can say that I want the exit temperature of the system to be such, okay, then the system will calculate it with an exit temperature of the value you have specified. Similarly, superheat temperature change also you can specify, and you have to specify the exit stream moisture content. Okay, so when we solve the problem, you will find the solid stream specified over here, because there may be various types of solid streams. Say you can use a conventional solid, you can use non-conventional solid. Even for conventional and non-conventional solids, you may have the solids with particle size distribution. You can have a solid without particle size distribution. So depending upon the type of solid stream, options will be open for you. And for each option, you have to provide the exit moisture content, either in wet basis or in dry basis. So in this drop-down menu, there are 2 options, wet basis or dry basis. Okay, so these are the things that you have to mention. Another thing is there here, PSD you may mention, you may not, because PSD is important for only spray dryers, because in spray dryer, the particle size distribution of the outlet solid, that is very important, because the liquid is sprayed and then solid particle is formed in the spray dryer. So outlet particle size distribution is the most important factor over there. But for other type of dryer, such as convective dryer or the shortcut or contact dryer, PSD is not that important. You can specify, if you want, you can specify, but it is not that important. And another factor is their entrainment. The entrainment means there are possibilities that during the operation, some of the lighter particles get detached from the solid stream and they are carried away by the exhaust gas stream. Okay, so some solid particles may be lost like that. So that is called the entrainment. So you may say that 0.01% of the solid particles are getting entrained by the gas stream. So that you can specify over here in entrainment. So that is how the specifications are given for shortcut method. For convective dryer method, you have to specify the geometry. So first you have to say whether the system is counter current co-current or cross-flow. I mean, whether the gas and solid flow in the co-current manner or counter-current manner or cross-flow manner, that you have to choose. And then you have to choose the input specification. So you have to choose two of either of them. So there are options for length, volume, cross-sectional area, solids residence time, and solid velocity. So either of two of them you have to choose, of which either volume or length is must. Either you have to choose volume or length, or you can choose both. But you cannot choose like cross-sectional area and solids residence time. You cannot choose like that. That option is not there. Okay. So input specification, that whatever you choose, based on that, these options will be open for you where you can set your data. Fill grade and bed porosity, generally the default values are taken and you may not have some values over it. If you have those values, you can give, otherwise you can leave them. Now, mass transfer data is very important. You can specify the mass transfer coefficient directly, or else you can calculate the mass transfer coefficient from Sherwood number. You can consult the Aspen help file. Here you can find the D32 means Sauter mean diameter of the inlet particle size distribution, and delta G is the diffusion coefficient of vapor in the gas. So these two information will be available, one from the property database, the other from the particle size distribution that you provide. And Sherwood number, if you provide over here, then the mass transfer coefficient will be calculated by Aspen Plus. Alternatively, if you provide the mass transfer coefficient multiplied by surface area, then the mass transfer coefficient will be calculated if you know NP and AP. This is NP and AP, their total number of particles, and AP is the average surface area of one particle. And these two things are calculated based on the data, and most of the data are obtained from either the particle size distribution or the property database, such as this solid density. Solid density is available from property database, and the particle size distribution, you can find out the dp, okay, xi, and ms dot, this is the flow rate of the solid. Okay, so these informations are there. So Aspen will calculate NP and AP, and based on that, as we have seen the equation before, it will calculate the mass transfer coefficient. Similarly, if you specify NTU, NTU means the number of transfer unit. So if NTU is known, other things also can be found by Aspen, like mg dot, it denotes the dry gas mass flow, rho g is the dry gas density, and AP and NP you know how to calculate. So if you fix the number of transfer unit, the mass transfer coefficient will be automatically calculated by Aspen Plus. So that's how the mass transfer coefficient is calculated. Similarly, for heat transfer between gas and solid, you need the expression of heat transfer coefficient. Now, you can directly specify the heat transfer coefficient if you know the value. Else, you can calculate the heat transfer coefficient from Lewis number. Actually, you have to give certain parameters such as the exponent n and heat transfer coefficient scale factor. Those two things if you provide, then Aspen will calculate the heat transfer coefficient. Now, how it will calculate? You can find over here. So, this is the heat transfer coefficient alpha g, which is related to The mass transfer coefficient beta G, already I explained how to calculate it. Rho G and CpG, that is density and specific heat of the gas. And this is the Lewis number. And how Lewis number is calculated, you can get it from this particular reference. If you want to see the reference, it is 19. So it is Sattler K and this book, Thermal Separation Process. So I have got a copy of that book. So thermal separation process of this book. So we have to go to page number 333. So let us go to page number 333. Yeah, so this is page number 333. And you will find the Lewis number over here. So this is the Lewis number, which eventually may be calculated by this. Here is the updated expression. So if you provide the exponent, that is n, okay, so this n you have to provide. So all other things are known. This lambda is thermal conductivity of the drying gas, density, specific heat and heat of conduction, and diffusion coefficient. These are all obtained from property database. So you do not have to worry about it. You have to just give the value of n. And once you give this value of n, you can simply calculate the heat transfer coefficient. I mean, the Aspen Plus software will calculate it for you. And then about indirect heating. So this is about indirect heating in convective dryer. So here also you can directly specify the heat input. You can say that I will supply 50 kilowatt of heat in addition to the heat or enthalpy that is carried by the heated gas. And you can say what is the fraction of input of that heat that is going into the solid. Because if you give the heat, then both the solid and the gas will be heated up. So what is the fraction of your supplied heat is actually going to the solid? That also you can specify over here. If you think that 90% of your supplied heat is going into the solid, then you just write 0.9 over here. Otherwise, Aspen can calculate the indirect heat input from this information. For that, you have to provide heat transfer coefficient between wall and gas, this one, or heat transfer coefficient between wall and solid, this one. And also you have to provide the heat transfer area and the wall temperature. And other things, that is the solid temperature, gas temperature, the length of the convective dryer, those things are known. And finally, the drying curve. Now you have to give relevant information about the drying curve, and those relevant informations are the solid moisture content, both critical and equilibrium, which are either dry basis or wet basis. So you know what is equilibrium moisture content and what is critical moisture content. So those two figures, whether it is in dry basis or wet basis, that you have to fix, and you have to provide this data over here. In addition to that, you have to provide the normalized drying curve model. So here you can give either the function or the data. Now what is the function? Again, you can go to the Aspen help file. This is the drying curve function. You will find the normalized drying rate. So this is the normalized drying rate against X, which is normalized moisture content. And another factor is there, excrete. Excrete means critical solid moisture content. So here you will get the normalized drying rate against X, provided you know this factor F. F is the only factor that you have to decide. And F is from 0 to 1. For various values of capital F, your drying curves will change. So in this case, the drying curve shape factor F has to be provided here, any number between 0 and 1, if you know the drying function properly. And if you do not know the drying function properly, suppose you have the data, raw data, then what you can do, you can simply choose data and you will get an option for a table like this. So a table will be open, and here against the normalized moisture content X, you have to provide the value of the drying rate. Both will be between 0 and 1 because it is normalized. Okay. So if you have the data, you can give the data, or if you know the shape factor, you can provide the shape factor. So this is how the convective dryer calculation can be set. Now next thing is the spray dryer. For spray dryer, height and diameter of the spray dryer is very important, and also the operation specifications such as pressure, at which pressure the spray is generated. So that information has to be given over here. And next information is particle size distribution. As I said, this is one of the most important factor for spray dryer because the end product of a spray dryer is small particles, solid particles or porous particle, whatever it is. And whenever the particles are there, we have to have some particle size distribution. So this particle formulation, there are various functions like spline, linear, distribution function. Okay, so this you can refer the help file. You will get to know what they are. So you have to specify which function you want to choose. Then in mass transfer and heat transfer, there is not much things to know. The adjustment factors are by default 1. But if you want, you can specify the spray zone height, because in the spray dryer, if it is something like this, the nozzles will be there. So the entire height is not used for spraying because the spray begins from the nozzle to the end. Okay, so the spray zone, what is the spray zone height? So that you have to fix. And there will be some correction because of this spray zone. There are two models. One is based on dead time, another is based on the tabular data. Okay. Now, if you choose tabular data, then this option will be open. So for every relative distance from the atomizer I will come later. Atomizer means from where the small droplets are forced out. That is the nozzle mouth. So relative distance from the atomizer, your mass transfer correction factor and heat transfer correction factor, you can place it in a tabular form. But these calculations are quite rigorous. Okay. For regular spray dryer calculations, such rigorous process may not be necessary. And then the drying curve, I have already explained, and atomization. So this is very important. There are two models. One is atomization model and the other one is user specified. Again, if you have a model of your own that you might have got from literature, or maybe you have developed a model by yourself, so that you can use. Else, you can use regular atomization model. And in atomization model, there are three options: hollow cone nozzle, two fluid nozzle, and rotary atomizer. Now, you can get all this information from the help file. So here it is. This is the spray dryer droplet size distribution. You can calculate it from the nozzle geometry. Now here you have hollow cone nozzles, and the sorter mean diameter of the droplet size distribution is calculated from this equation. Okay. What are the things that are unknown to you? You have to specify the nozzle diameter. So this nozzle diameter you have to specify over here. And you have WE and OH. What are they? WE is Weber number and OH is Ohn-Sorge number. So these two things you have to calculate. How they are calculated? Based on these quantities. And their viscosity, surface tension and density of the liquid, all of them are obtained from the property database. And for Weber number, you want VA, which is exit velocity from the nozzle, and this is calculated from the potential velocity in the absence of losses, which comes from Bernoulli's equation for incompressible fluid. So this is the data Vpot, that is the potential velocity, and it is from delta P. Delta P is the pressure drop, and you have another factor, that is the correction factor, coefficient phi. This is typically from 0.8 to 0.9. Okay, so these values you can check. Similarly, another factor is there, kappa. For this kappa, you can check what is kappa. You can calculate from these values, where theta is there. Theta is the full spray angle. Okay, so this full spray angle in degrees that you have to give, whether it is the spray angle is 30 degree or 40 degree or whatever. So that you have to provide. And all other information such as the volumetric flow rate per nozzle, they are all defined by number of atomizer and orifice diameter, droplet interval. In short, if you provide these data, all the calculations will be done by Aspen Plus itself. Okay, so this is by hollow cone nozzle, and there are two fluid nozzle also. For that, you have to give an extra information on fluid mixing and how they are calculated. You can find it from here. Two fluid internal mixing nozzles. Okay, so with some extra parameters such as these two, you can calculate with the help of Aspen Plus. And next one is the rotary atomizer. So rotary atomizer looks like this. So this is atomizer wheel, and these are the blade heights. And blade height you have to provide the wheel speed in RPM, because the atomizer it rotates. So RPM you have to provide, and number of blades, how many blades will be there, that also you have to provide, and the atomizer wheel diameter. So diameter you have to provide. So if you provide all this information, basically the geometry of that, then from this set of equations, you will be able to find the required specifications. Okay, so that's how the spray dryer is specified. And then you have contact dryer. In contact dryer, you have to specify the length of the contact dryer, and also you have to provide the mass and heat transfer options. Here you can specify the indirect heat input, say 50 kilowatt or so, or else you can give certain data like heat transfer coefficient between wall and solids. Suppose this is the heating plate, okay, and here you have the solid. So what is the heat transfer coefficient between the wall and the solid? That you can specify Then heat transfer area of wall and solid. So what is the area across which the heat transfer is taking place? And wall temperature. So this is the TW. So if you specify them, then Aspen Plus will calculate the total indirect heat input that is given. And also you have to provide some information between the heat transfer between the gas and solid, because the gas is still going in and gas is taking the moisture content from the solid and going out. So the heat transfer coefficient between gas and solid you have to provide, and heat transfer area of gas and solid, that also you have to provide. Or else you can assume that there are thermodynamic equilibrium between gas and solid. If you consider thermodynamic equilibrium, that also is allowed. Aspen Plus will accordingly calculate the equilibrium condition based on the other data given. And for batch mode, there is only one option, that is convective dryer. And for that you have to provide this information. Either you have to provide batch charge or you have to provide batch feed time. And batch discharge time and batch downtime, if any, that also you have to provide. Mass and heat transfer, that is very much similar to whatever you have learned in continuous convective dryer problem. And similar thing is for drying curve as well. So there is nothing new in it, similar to the continuous case. Now we will take a example problem and try to solve it using this dryer model. For that, let us see the example first.